Welcome to Pre-Calculus. Today we will investigate finding partial sums of arithmetic series. We'll take a look at 4 examples. Our first example is given as a sequence, and I know it's a sequence because it's numbers separated by commas. And my instructions tell me to evaluate the related series of the sequence. The first thing I want to do is rewrite this as a series. And that really is down to replacing the commas with addition. Remember, a series is a list of values that are added together. And to evaluate this with a series that's short, like this one only has 6 terms, I can probably just add these numbers together. So a good way to do that is to pair them up. 13 plus 16, that's going to give us 29. 19 plus 22, that's going to give us 41. And 25 plus 28, that's going to be 53. If I add together 29 and 41, those are going to add up to 80. Let me adjust that. That's going to add to 70. And then 70 plus 53 added together is going to give me 123. So for a series that's a small series, only 6 terms like this one, it's easy enough to just add up the numbers. But one thing that we should consider is how we would do this same task for a series that had more terms. And so we're really looking for a formula or some kind of equation that we could use. And we're in luck. We have a formula for adding up the first n terms of an arithmetic series. And it's given by this equation: S sub n equals n divided by 2 times the sum of the first term, a sub 1, and the last term, a sub n. Let's use this to check, since we know that this series adds up to 123. So I would set up by putting in the number of terms. So we'd already said there were 6 terms, so 6 divided by 2. And then I just need to grab my first term, that's a sub 1, that's 13. And my nth term, which in this case is the last term, 28. And I just want to calculate that out. So 6 divided by 2 is going to be 3 times 13 plus 28. That's 38 plus 3 is 41. And 3 times 41 is going to be 123. So definitely that equation confirms the answer that we got here just by adding the numbers up, and really is a useful tool for us as we go and try to evaluate a more complex series. Our second example is given with sigma notation. So this is a very condensed way of representing a series. If we were to unpackage it, it says, what's the sum from the first term to the 14th term using the explicit formula 10i minus 19? Just to get a feeling for what this series looks like, it's got 14 terms. So 1, 2, 3, 4, ... 13, 14. So I'm not going to list everything out, but it's got quite a few more terms than our previous one. Let's just generate a few of these terms. So I would calculate them by plugging in the n value into the explicit formula, 10i minus 19. So my first term is going to be 10 times 1 minus 19, which is going to give me -9. So that's our first term. Again, we would just take and plug in my first n value, which is 1 minus 19. So that's -9. And I see that by this common difference, which is showing up as my slope, if I think of this as mx plus b, that 10 is like my slope, I'd really just add 10 to each term to get the next one. So -9 plus 10 is 1. 1 plus 10 is 11, 21, ... so forth. And really we could calculate the 13th and the 14th by plugging in their values for the I, or the n in this case. So I'll plug in 14, that's 10 times 14 minus 19, that's 140 minus 19. So the nth term, the 14th term of this series is going to be 121. So we've skipped some of the middle terms, but again, for me to evaluate the arithmetic series, I've got a formula that really only needs the first and the last. So let's set it up. I want to calculate the sum of the first 14 terms. So again, my formula is n divided by 2. In fact, let's put it in general terms first here. So S sub n equals n plus 2 times a sub 1 plus a sub n. And that's what we're calculating here. So again, I'll specify the sum of the first 14 is 14 divided by 2 times the first term, -9, plus the nth term, which is the 14th term, 121. So we'll just calculate that from the formula. That's 7 times -9 plus 121 is going to be 112. And then 7 times 112 is going to be 784. 784. So definitely an advantage to have a formula. When I have a lot of terms like this, 14 terms are a lot to list, and then let alone add up. The formula saves time. It also saves opportunities where we could make an error. Let's take a look at number 9. So this example is different from our previous sigma notation series in that it does not start from m equals 1. It starts from m equals 3. So my formula only works when I'm calculating the sum from the first term to the nth term. So if I'm trying to start at some other term, in this case the third term, I really need to rewrite my initial sigma notation as the difference. So essentially I need to account for the two terms, the first and the second, that are missing here. And the way that I would set this up is I would consider the full series from m equals 1 up to 12. So notice I'm including the two terms that were missing in my original of -25 over 12 plus 4/3 m. But then I need to take away or subtract the two terms that are missing. So I would take away the summation from m equals 1 to 2 of the same explicit formula, -25 over 12 plus 4/3 m. So I do have two of these to calculate. So again, I need to just remember how I'm going to set this up with the formula. So it's S sub n equals n over 2 times a sub 1 plus a sub n. And then we're going to do the same thing, but for the dimensions of this second one, the sigma notation that would represent the sum of the first two terms. Now the parts that they will have in common are the first term, a sub 1. The other pieces will vary according to the sigma notation. So for this first one, if we're going to set it up, I'm going to put my n value as 12 over 2. I can set up the second one as well, minus this one, the n value is going to be 2 over 2. And let's find that common piece, which is the first term. So to do that, I'm going to come back over here to the explicit formula. I'm looking for a sub 1, so I'm going to plug in 1 for the m. So it's -25 over 12 plus 4/3 times 1. 4/3 times 1 is just 4/3. And so I need to add up these two fractions, but they need to have the same denominator. So I'm going to scale 4/3 by multiplying it by 4 above and below. So that's 16 over 12. And that gives me this first term of -9 over 12, which I can reduce to -3/4. And that's going to go in two spots. That is the same first term for both of my sigma notations, the full one and then the two terms that I'm adding together and then taking out. So then what's left for me to find is the nth term of each of these series that I've kind of separated. They are different. So the nth term for the one that's represented by this purple to stand for the whole series would be a sub 12. So to calculate that, I'm going to take the same strategy as I did to find a sub 1. I'm just going to plug in 12 for the m value instead of 1. So it's negative 25 over 12 plus 4/3 times 12. So that's going to reduce 12 divided by 3 is 4. 4 times 4 is 16. So that's negative 25 over 12 plus, and then I want to call 16 something over 12. So that will be useful to calculate here on the screen. So 16 times 12 is going to be 192. So then I just need to add my numerators. Negative 25 plus 192 is going to give us 167. So that a sub 12 is going to be 167 over 12. So that completes that first setup. The last thing for me to calculate before we find the full sum here is my nth term for this red series. So that's just the second term. So all we got to do is calculate a sub 2. So that's negative 25 over 12. This is familiar at this point. We're using the same strategy a third time, times 2. So that's going to be negative 25 over 12. That's going to be 8 over 3, but I need to multiply and scale it so that it's got denominator 12. So 8 times 4 is going to be 32. And 32 minus 25 is going to be 7 over 12. And that completes the setup. So at that point, what I want to do is calculate it. And just thinking about a strategy to find the calculation, the setup is very rational, lots of fractions. In fact, each one's a fraction. So I could, as we've done in previous examples, just crunch the numbers. But I think it's going to save time to input this into a calculator. So I'm going to head to Desmos. And let's enter the expression that we've written and let Desmos simplify the fractions for us. So here we're going to enter 12 divided by 2. And we'll expand our screen. Times negative 3/4 plus 167 twelfths minus 2 divided by 2 times negative 3/4 plus 7 twelfths. And that's giving me 79.16 repeating. I could write that as an approximation. That gives me a good sense about the rough dimensions. I want to convert to an improper fraction. So that has the exact value of 475 divided by 6. So good opportunity to take advantage of the calculator for a very rational sum here. So in the end, our final sum here is going to be 79.1 repeating 6, or 475 divided by 6. Let's take a look at one last example that is a word question. So here I have a real life scenario on a Sunday after a minor surgery. A woman's able to walk a half mile. Each Sunday she walks an additional quarter mile. After 8 weeks, what will be the total number of miles she has walked? So to set this one up as a series, I just want to consider that the n values are representative of Sundays. And the woman that we're reading about walks over a period of 8 Sundays. So I'm going to represent those with these 8 n values. She begins by walking a half of a mile. So I'll represent that as 0.5. And then every Sunday, she walks the original half mile, but adds a quarter mile to it. So on the second Sunday, she's going to walk 0.75 miles. And she continues to add a quarter mile. So on the third Sunday, she walks 1 mile. The fourth, she walks 1 1/4. The fifth Sunday, she walks 1 1/2. The sixth Sunday, she walks 1 3/4. The seventh Sunday, she walks 2 miles. And the eighth Sunday, she walks 2 1/4 miles. So that's really the representative of the series. So if I wanted to make it a series, I'd include addition between the distance values. Now I want to include a sigma notation expression to represent the partial sum. So I'm going to write that here. It's sigma from n equals 1 to 8. And then I need to write an explicit equation to represent this arithmetic series. So to do so, remember, I'm going to pick up the template a sub n equals the first term plus the common difference times n minus 1. And we'll plug in our first term, so that's half, 0.5, plus the difference, and that was the quarter mile that we added each time. So 0.25 times n minus 1. I'm going to distribute the quarter through the n minus 1 binomial. That gives me 0.5 plus 0.25 n minus a quarter. And then I'll always have constant terms that I can combine. So this is ultimately going to become 0.25 n. 0.5 minus 0.25 is 1/4, so 0.25. And that is going to form my sigma notation expression. 0.25 n plus 0.25. I'll box that since that is part of my answer is the sigma notation expression. But then I want to answer the question, which really is finding the partial sum. So I want to calculate here what is the sum of the first n terms. There's 8 of them. And this is the same equation we've been using with our abstract question. So it's n over 2, 8 divided by 2. And then I've got the whole series listed out. I can just easily grab the first and nth terms there. So it's going to be 0.5, that's the first distance, plus 2 1/4, 2.25. And we just need to calculate. So this is going to be 4 times, if I add half and 2.25, that's 2.75. And then 4 times 2.75 is going to give me 4 times 2 is 8. 4 times 3/4 is going to be 3. 8 plus 3 is 11. And my units here will be miles. So just to tie it to our scenario, the total distance that the woman has walked over a period of 8 weeks is 11 miles. Thanks for joining for this investigation of finding partial sums of arithmetic series. Thanks for joining. See you soon.